Cool, let's get started. Thank you guys for coming to the third Compass lecture of the semester. Today we're happy to have Peter Petrov and Jessie Zhang, who are two postdoctoral researchers in physics. We'll be talking about improving electron microscopy with an ultra-high intensity laser. Jessie completed her undergraduate studies at MIT and obtained a PhD in physics at Harvard University, working in the area of experimental atomic, molecular, and optical physics. She has been working as a postdoc in the group of Holger Muller in the physics department at Berkeley since 2022. Peter is originally from Bulgaria, but moved to the US with his parents as a kid. After finishing high school in Oklahoma, he got a bachelor's degree in chemistry from Cal and a PhD in chemistry from Stanford. Since 2020, he has been back at Berkeley working as a postdoc with Holger Muller's group in the physics department. Please join me in welcoming Peter and Jessie.
Thanks. Thanks to you guys for coming and for those on Zoom as well. So our talk today is about our project that we're doing in Holger Muller's group. So this is about improving electron microscopy with a ultra high intensity laser, which is kind of a counterintuitive maybe thing to hear at first, because electron microscopes and lasers are not usually things that people work on at the same time. So in this talk, we'll tell you about what it is that we do specifically. Hopefully you'll understand this picture here on the left by the end of the talk. Maybe, okay. But to give you kind of a sort of walkthrough first of what we plan. So first of all, we're going to talk about a little bit of motivation behind the talk. So the sort of central motivation behind our research is that we want to improve visualization of biomolecules. So there are a number of ways that someone could do that. We took a page out of a lecture from Richard Feynman in 1959. He said that one thing that would benefit biologists a lot is to make the electron microscope 100 times better. And so we've chosen to sort of pursue that of making the electron microscope better to visualize biomolecules in particular. So the rest of the talk will kind of go into a little bit of introduction of wave mechanics and comparing light and electron microscopes. Light microscopes are, of course, a lot more familiar to people in general, but they help us understand electron microscopes. And in particular, that'll lead us into understanding phase contrast imaging, which is the way that biomolecules are observed in a transmission electron microscope. And then we'll go into the laser faceplate. So that's our ultra high intensity laser in the title. So we interact the laser with the electrons, and that improves the contrast of the microscopes. We'll talk about how that happens and how the cavity is made and how it works. And then we'll show some of the experimental results of actually building this device and integrating it into electron microscopes in our lab. So feel free to stop and ask questions at any point. But for now, we can get started. So electron microscopy has a certain advantage that we like, which is that we can give context to structural biology. So what I mean by that is that we can take something, a living system, such as, in this case, sperm whales. Sperm whales are a very large organism. And one cool thing that sperm whales can do is they can hold their breath underwater for a very long time. And so the way that they do that is that they store oxygen in a molecule called myoglobin. And it would be interesting, has been interesting to study how that happens by looking at the molecular structure of myoglobin. And so as early as the 50s, that structure was determined via X-ray diffraction. So a crystal of myoglobin was made, and then X-rays were used to collect a diffraction pattern and to determine the structure of myoglobin molecule. There are other structural biology techniques like nuclear magnetic resonance, which involves making a purified solution of protein, and a little tube of NMR tube is shown there on the right. And so then you get your myoglobin structure out. And so this is a small molecule. It's about 3 nanometers for a protein. It's it's a few hundred atoms in total here, all connected together. But the main thing that this protein structure doesn't tell you, the most obvious thing that it doesn't tell you, is the context of the molecule. So this artistic rendering here on the left is something sort of familiar to everyone. It's the way that COVID binds to a cell membrane and transmits its contents. So this is a drawing, of course, it's not data, and it's colored to show you all the different variety of particles that exist in this big sort of ecosystem of this biological system. And so the one protein structure is just a small facet of what's going on in here. And of course, this is all dynamic too. So that's something we won't even get into today. But Suffice to say that proteins aren't isolated in real life. And so what we want to do is use EM to visualize biomolecules in their context. So I'll turn it over to Jessie, who will tell you about waves.
Yeah, so before we delve into microscopes, I thought we'd first give a little primer or review on some basic wave mechanics, because a surprising amount of all the rest of the talk will boil down to some simple concepts just from wave mechanics. So as we know, waves are everywhere. It's how you're hearing this talk right now. It's how you're seeing these slides. You can see it on in a pool of water. And if you abstract it out, what's common to all of these phenomena is you have some oscillatory behavior, and that travels down some direction. And some key concepts here, one is the amplitude of this oscillation, that sort of gives the power in this wave. The wavelength is like how much, like the period in this wave. And if you have two waves traveling alongside each other, there's this concept of a relative phase between them. So we'll come back to these concepts a lot in this talk. One key phenomena that wave exhibit is interference. So for example, if you have two waves with the same wavelength, and they're propagating together, what you end up with is a superposition of the two waves. So you sum up these two waves, and depending on the relative phase between the two waves, you can get either what is known as constructive interference. So this is when they're exactly in phase and they all sum up to get something bigger. Or if they're exactly out of phase, then they exactly cancel and you end up with no wave being transmitted at all. And of course, you can have something in between, like a phase difference, and you get an amplitude that lies somewhere in between. And so, for example, these ripple patterns you see from these two separate waves is an example of this superposition of the waves. And this is one of the defining characteristic of waves, so much so that when we try to understand, is something a wave, this is one of the key phenomena we try to look for. So for example, we know that light is a wave because one of the things it will do is if you send it through two thin slits and have it propagate, you'll see an interference pattern that is characteristic of this superposition principle. And so people were surprised when, in fact, actually electrons also behave in a similar way. So if you send electrons through two slits and on a screen, you also observe these peak-like structures that are characteristic of waves. So I won't go into the details of exactly, these particles and how you think of them as waves. But for this talk, all you need to know is that light and electrons, we can think of them both similarly as waves. Light is oscillating electric and magnetic fields that propagate along some direction. And it actually spans a broad spectrum. So what we see as light has their wavelength is approximately in the hundreds of nanometer range. And so that lies here along the spectrum, but the radio that we listen to, microwave ovens, X-rays at the hospital, they all fall into this. It's all electric and magnetic fields as a wave phenomenon. And as I mentioned, electrons, we can think of them both as a particle and a wave, and we'll actually be using both of those pictures in the rest of the talk. And one crucial point is that the wavelength of electrons is on the order of picometers. So that's 10 to the minus 12 meters. So 3 orders of magnitude, even smaller than a nanometer, which you probably are familiar with.
Okay, so with that understanding of waves, we can think about how a microscope is actually built. So a microscope is probably a familiar object. This is an example of one of mine. It has a light source at the top, and then you send the light source through a series of lenses, and then eventually that hits your eye or it hits a camera. And the main sort of operating principle is the lens. So the lens is a piece of glass, usually for light, that refracts the light, bends the rays, as you can see in this illustration, so that when light comes from a point on the object, it creates a similar point on the image that relays that information and can form whole images. Importantly, though, we have to figure out what is the contrast mechanism that actually makes features of the sample appear in the image. So the most obvious one is amplitude contrast. So that's shown here with this picture of some tissue paper. So the idea is that we send some light through the sample. Some of the light just passes through the tissue paper and doesn't actually reach any of the sort of filaments. It's not obstructed in any way. So you see that as a light signal. And then you see less light where the light was absorbed or scattered by the tissue paper. Another thing that can happen is you can have phase contrast, which is where the sample actually phase shifts the light. And as a result, the background now, the part where there is no sample, is gray rather than white. And instead, the white and the black are coming from interference patterns created by the phase shift of the light by the tissue paper that's in its way. So the idea is that we take our medium, our light or our electrons, and we impart some phase shift and create an image by wave interference. And an important property of the microscope then is the wavelength. So the wavelength of the light or the electrons determines the smallest spot that you can form. So even if I have a point object that's infinitesimally small, it will make in a microscope, it will make an airy pattern. This is this disc shape that has these sort of concentric rings around a central spot. And the dimensions of that pattern are going to be about the size of the wavelength. So that is kind of the best case scenario, really. So what's important is if you want molecular structures, if you want to look at something that's 3 nanometers in size, you need something with a small wavelength. And so visible light at a few hundred nanometers is just not going to cut it. And the other thing that's important is that the smallest distance between 2 objects that can be resolved is related to this wavelength. And so here you can see how as I bring 2 points closer together, at a certain point, their airy disks overlap to the point where I can't actually distinguish that there are 2 objects. So that's what we call the point resolution of the microscope. And so if we rule out visible light because of its long wavelength, we could think, okay, what about shorter wavelengths of light? The problem with shorter wavelengths of light in general is that they tend to be hard to work with. It's hard to make optics that work, lenses that work with wavelengths that are so small. X-ray diffraction, for example, gets around this by making a diffraction pattern instead of an image, and you can still get the high resolution structure out of a diffraction pattern. But another way that we'll focus on is using electron microscopes. So these actually have a small wavelength, electron wavelength on the order of picometers. So we can use this to make a high resolution microscope because we can actually make a lens for electrons. Electron lenses look different. They're not pieces of glass, right? They're actually using the Lorentz force. They're using electric and magnetic fields to shape the trajectory of electrons so that you produce an image in a similar way, very similar way to how light lenses, optical lenses make an image. And so this up in the top right here, you can see a coil of wire and running a current through it produces a magnetic field. And we wrap that coil of wire in some magnetic material to sort of sculpt the magnetic field at a particular position. And then the electron passes kind of through the duct and all the way down, and that produces the focusing action of the lens. So then we can stack those together in a big column. And that's what you see on the bottom is an example of one of the electron microscopes in Stanley Hall. So, the other thing that we have here as a sort of free parameter is the electron wavelength. So we can vary the electron wavelength simply by changing the velocity of the electron. The electron's momentum is related to its wavelength as it's inversely proportional to the wavelength. And so, of course, the momentum is related to the kinetic energy. So by simply accelerating the electron to a different, through a different voltage, we can change the wavelength of the electron, and we can set in that way the interaction that the electron will have with matter, and we can also set the properties of the microscope. And so the electrons will, of course, interact with atomic nuclei. They'll be attracted to nuclei, and they'll also be repelled by electrons. So they're sensitive to matter, right? And in this way, a biomolecule composed of mostly light atoms like hydrogen, carbon, nitrogen, and oxygen can apply a small phase shift and imprint its information onto the electron beam. And so then when we form an image using that wave that carries this phase information, we can observe contrast. We can observe the molecule. The main limitation that prevents us from just using this as a great tool all the time is that we actually need to accelerate the electrons to a very high, through a very high voltage. So we accelerate them to 300 kilovolt, which brings the wavelength down to 2 picometers, which is definitely sufficient for looking at bonds that are 10 times that. So the problem that we have is that the electrons will damage the sample as they pass through. And so a typical chemical bond is going to be about 5 electron volts in energy, whereas the accelerating voltage is going to carry 300 kilo electron volts. And so that means that when we look at a biological sample, we're going to get lots of side effects. Even if we have a sort of weak interaction, because we're sending many hundreds, thousands, millions of electrons through the entire sample, we end up causing a lot of damage. And so this is an example of imaging a virus particle and sending a number of electrons through. And you can see how these sort of pores start to form. And so this is the formation of gaseous products that are formed by ionizing various bonds and then allowing chemistry to happen. And so this is, of course, not what we want. To get a high resolution structure, we need the thing to be relatively pristine. And so we are limited to this sort of first case on the left where we have very few electrons. And so since we're forming an image with very few electrons, we're going to be stuck with a low signal to noise ratio. And so that means we need to maximize the contrast. To illustrate how that works, I have a simulation here of apoferritin, which is a particle you'll see again. So apoferritin is this sort of sphere-like particle. And if you change the properties of the microscope, you can change the contrast of the image. So here I'm plotting this as the relative probability of detecting an electron in a given place, where 1 is the probability of detecting an electron away from the particle. And you can see how one of these, the one on the left, has lower contrast, right? The sort of difference between the light and dark in the image are smaller. And what that means is now if I vary the signal to noise ratio, that when the contrast is low, the particle will sort of disappear from the field of view before it does for the high signal to noise ratio, for the high contrast case. And because we're stuck with a low signal to noise ratio because of the radiation damage limit, then one way that we can improve the images in cryo-EM in electron microscopy is to just enhance the contrast. Yeah.
Sorry, in this case, is most of the probability solely from just going through more matter? What is the reason that those edges are more probabilistically?
So there are one way to reduce the signal to noise ratio is to go through more matter. Another way is in this case, I suppose that's the main thing that's changing. What I'm changing to change the contrast in this calculation is I'm changing actually the microscope parameter. So the sort of phase contrast image is changing the wave interference on the right versus on the left is what you would get in a conventional image.
Yeah, I think I was going to ask you about the former, like how the electrons actually appear are more probable to make the image. What is the main limiting factor?
Right.
And that's the matter that's.
Yeah.
So more matter is bad for us.
Right. You're going to scatter off of more matter. You're going to deposit more energy into the sample, which also has those downstream effects. Yeah.
What's a typical sample look like? Like, oh, it's a cell or some biological matter.
Yeah, that's a good question. So we're kind of glossing over that, I think, in this presentation, but it's basically found that biomolecules, because of these sort of products that form and the mobility of the ionized products that form and sort of do chemistry, it's found that freezing the sample, so plunge freezing it into like a solution of liquid ethane, will sort of vitrify the water that the sample lives in. So the sample is living in some water or some buffer, some aqueous solution, and you freeze it instantaneously as fast as possible, but in a way that doesn't crystallize the ice. So you still have this kind of amorphous water structure that you would have normally. But now you have this thing in a sort of thin film, so 100 nanometers thick, and then it's composed of some number of proteins or whatever you are interested in. So sometimes you look at purified proteins, but you can also take a section of a cell and freeze it. And you usually have to mill that down because it's actually hard to pre-prepare a section of a cell at 100 nanometers and then freeze it. So they'll make it like a micron and then they'll cut it down. But yeah, it's a great question. Yeah.
Yeah. So Peter showed these simulations of how, the images you get vary drastically between low contrast and high contrast. And so the next part of the talk, I'll discuss how we can, how a microscope can go from this low contrast to a high contrast image taking state. So, okay, this color is weak. As I mentioned, so these electrons, we can think of them as waves. We pass them through some sample. And part of that, so in a microscope, these electrons, part of it goes unaltered by the sample and just passes straight through. So this is what we call the unscattered beam. Part of it does interact with the sample. You've got stuff in the sample. And as Peter mentioned, that introduces a phase shift on the electrons. And so that's shown here. This is the scattered beam with this tiny little phase shift. And what happens on the detector is that these two beams interfere to produce the signal that a signal that you can measure. Now, the difference between, say, some part with that interacts more with the electron and less introduces different amounts of phase shift. So if you got more stuff, that introduces a larger phase shift. And when it gets interfered on the detector, you get another wave that you can see there's a tiny bit of difference in the phase and the amplitude when you form the superposition of these. And an image would look something like this. And in reality, so if you can't see anything, it's not because it's because there isn't anything like you like this is just a really small signal to be trying to look for. So how can we do better than this? So it turns out if we have a way of phase shifting the beam exactly by half a cycle, so half a wavelength, right here. So we focus down the scattered beam and shift it right over here so that our unscattered beam now has this half a cycle phase shift. Then we interfere it with these different parts of the sample. What happens is we see a much better difference between if there's more or less stuff in the sample. And so this is what we mean by better contrast. And so what we need here is what we call a faceplate. And with something like this, just as a sneak peek of the data, what you get is you can turn something like this into this. And this is all in hardware. So, this isn't applying some image processing to this. This is completely with the use of, we do some magic here and you can get these much better images. And in our experiment, what we do to do this magic is we send a laser in. We need a very intense light beam to interact with our laser, with our electron beam. And we call this the laser faceplate. So for the next part, I'll discuss how this all happens. So as I mentioned, light is an electromagnetic wave. So you've got oscillating electric fields. And when an electron passes through such a field, it will interact with this oscillating electric field. And so say at a point, your electric field is oscillating back and forth, that electron will feel that force and oscillate back and forth. So in a homogeneous field, what you get, so say this is an electron, your electric field is oscillating back and forth. It's sort of like you're just oscillating back and forth. And ultimately, the electron stays where it is on average. The motion averages out to 0. So you can think of this as if you're on a swing and you're getting pushed from both the back and the front. You get a kick when you hit the back, you get a kick when you hit the front, and you're being kicked equal amounts on both sides. And on aggregate, you're still, you're just going back and forth in the same place. Now suppose you have a field that varies over like spatially. So you have some areas where the oscillation of this electric field is strong and parts where it's weak. Then what happens is that every time, say you're similar to this swing analogy, when you're at the front, you get a really strong kick, and when you're at the back, you get a really weak kick. And after enough cycles of that, you end up towards the part where you're getting a weaker kick because you're not being kicked back as much. So this is what we call the ponderer motive force. So the electron experiences a force towards the weaker areas of this electromagnetic field. And this is what we use in the microscope to generate the phase shift on the electron beam. So this, so we send it here and have it interact with the electron beam. Now the ponderer motive force is really, really weak. So we need on the order of 100 gigawatts per centimeter squared here at the center of the electron beam, or that's roughly 80 kilowatts of power. And just to give a sense of numbers, so these probably don't mean anything to you, but sunlight on a sunny day on Earth is probably on the order of 0.1 to 1 watts per centimeter squared. Now we need hundreds of gigawatts. Yes.
What's the cross-sectional area of the laser faceplate and the electron beam? Is it really, really small or reasonably big?
That's a good question. So we sort of can choose, but in our case, we want it to be as small as possible so that it's as intense as possible. Yeah, I'll get to that in a later slide. Yeah. Yeah, a typical laser in the lab, sort of the maximum power we can get is on the order of 100 watts. And so typical intensities we work at are roughly 1 gigawatt per centimeter squared. And that's still 2 orders of magnitude from what we want. Industrially, there are lasers on the order of tens of kilowatts. The military apparently has these weapon lasers that can go to 30 kilowatts, but those are like a huge truck. We don't want to use that in the lab. So none of these really get to the power that we need to generate this ponderer motive force that we want. So our solution is that we take a normal laser we can get in the lab, which is on the order of tens or 100 watts, and we amplify that using what is called a resonant cavity. So what is a resonant cavity? So imagine you have some light and we send it to 2 mirrors. And now these 2 mirrors are partially transmitting, but they're mostly reflecting. And we call this a cavity because it's just empty space in between 2 cavities. So when the light hits the mirror, part of it gets transmitted and goes through into the cavity. Now, when it hits this other mirror, part of it, again, gets transmitted, but I'll leave that out. But crucially, a large part of it gets reflected. And you get light traveling backwards. And the reflected light, again, will reflect off of this mirror, and you in turn get the light just circulating back and forth inside this space. So what you get is light going in and waves traveling in opposite directions, just circulating. And remember this concept of interference of waves. So when you add up these individual waves, what happens is actually you get what is known as a standing wave. If your mirror, like this cavity, satisfies certain properties where the wavelength or the length of the cavity is an exact multiple of the wavelength. So this is what we call a resonant cavity, and it forms standing waves. And a crucial property we use here is that if these mirrors are tuned properly, it results in an amplification of your initial light going in within the cavity. And this is kind of how microwave ovens work. So inside a microwave, there are standing waves of these microwaves, and that amplifies the signal. And so that's also why you need a spinning, like a rotating plate, so that you don't always sit somewhere where there's never any power. Yes.
If the wavelength is like kilometers, do you have to be able to just your mirrors like with that precision?
Yeah. So picometers is the wavelength of electrons.
Oh, yeah.
For light, so the particular light we're using is a micron or so. But yes, so we would need to adjust it on the order of like nanometers or tens of nanometers. Yeah. Any other questions? Yeah, so in reality, so here I showed these mirrors, they're sort of like flat. In reality, what we do is we actually have a slightly curved surface for these mirrors so that we can focus it to a very intense spot at the center. So hopefully that answers your question. And this is just so that we get a more intense beam to interact with the electron. And this is an example of the mirror, just for scale. So those are 2 fingers holding it. And the cavity looks something like this. So light would go in from one direction, and this is one of the mirrors. There's another mirror on the other side, and that forms the cavity. Because we're dealing with really, really high intensities, these mirrors need to be really, really clean. So there's a process to get mirrors to be really sort of flawless, called super polishing, where they just grind the mirror so that they're almost like atomically flat. And that's really what we need, because any slight defect in these mirrors will just burn under such high intensities. And we would never actually handle a mirror like this. Everything needs to happen under a flow bench and with tweezers, because these are really delicate and we don't want any dust or any residue landing on these mirrors. It also needs to operate in vacuum, again, because we don't want any sort of contamination on them. So we put it in a vacuum chamber, and this is an example. So this hole you're seeing here is where the electron beam would go through the cavity, and the mirrors are here and here. That forms the cavity that the laser light goes back and forth. Oops. And we also have some surrounding optics that actually sends the light into this cavity. And to the best of our knowledge, this is the world's most intense continuous wave laser. So at the center in there. Yes.
What material is the mirror?
It's made of what is it?
The special glass, the ultra low expansion glass.
Yeah.
It's like a product that's designed to sort of minimize thermal expansion, because there's so much light hitting the mirror that thermal deformations are a big issue. And then it's coated with a layer of sort of a stack of 2 materials that have different refractive index and make a sort of reflective grating. So there's kind of a similar phenomenon. To make a really high reflective mirror surface, you can stack 2 materials so that there's basically destructive interference for the wave that would go through, which means everything has to come back. But yeah,
I guess that material explicitly burn. I was assuming a lot of things would just burn if you put that laser in. It's designed not to high laser just going through it.
Yeah, one thing is that the laser spreads out a little bit, so you can see in the drawing that it's defocused by the time it actually hits the mirror.
And also, so these mirror substrates themselves don't actually see the hundreds of kilowatts power, because like all the light is being reflected at the front surface. So we're only sending in maybe 10 watts, but we're getting 80 kilowatts at the center because of this amplification. Yeah, so this is a photo of how it looks like on the benchtop when we do testing. So this is this vacuum chamber. In the next part, Peter will tell you how it's actually integrated into the microscope and what we see.
Yeah, so the lab looks something like this, which is like the electron microscope photo that I showed before, but our instrument is taller. We have an extra set of lenses that we use to actually insert the device into the microscope and sort of magnify the electron beam a little bit. But so for a little bit of orientation, the electron gun is at the top. So the electron source is at the top, and the electron's coming down. It goes through the sample indicated there, and then it continues on down to the floor where the camera is. And in between the sample and the camera, we have our laser faceplate, as Jessie's drawing showed. And so the faceplate itself is actually inserted into the column. So it sits on a long rod that we slot in through a hole in the column, and it sort of like dangles in the way of the electron beam. And then we send in the laser. So we have these two laser breadboards that we've strapped to the side of the microscope, which is also pretty unconventional. And the point of those is to actually just sort of shape the light that goes into the cavity and out of the cavity. So operating this cavity and stabilizing it is really demanding. We have to make sure that the cavity actually remains at the right length relative to the wavelength of the laser. So we can tune both the length of the cavity and also the wavelength of the laser. So we have this laser system, and it's also being controlled by some feedback electronics that basically monitor the cavity and make sure that everything stays stable while the electron beam is also passing through it. So they're kind of two separate systems. You know, the laser cavity is intended to just provide this high power, and then the electron beam, we use deflectors inside of the electron microscope to control where the electron beam goes so that they actually intersect the right way. So then we can start taking data. And one of the coolest things I think that we can do is, instead of sort of normal photography where you take the interaction that light has with matter and then you look at light on your detector, we're doing the opposite thing. We're taking matter and we're seeing the interaction that it has with light, and then we're forming an image using those electrons that hit a camera. And so you can actually see an image of a laser stripe, which is not something you can normally do. You might be able to see an image of dust scattering off a laser, you know, in a cloud or something. But in this case, the laser is actually just going through vacuum, and you can still see it because the electrons are what's forming the image. And we can zoom in on it, and you can start to see the standing wave structure here of the laser. So you can see the areas of high and low intensity are oscillating, and you can zoom in further and further still, and you can really see the laser standing wave really nicely. So one of the nice things about this is we can actually just look at the laser faceplate using the microscope and make sure that the properties make sense and are consistent with what we think they should be. But of course, the ultimate goal is to do the bioimaging. So this is an example again of that apoferritin protein. And these are just blown up versions of the images you saw earlier. So this is with the laser off, and then looking at the same sample with the laser on, hopefully. There it is. Oh, I skipped one. There it is. With the laser on, you can see the circles much more clearly, right? The contrast is significantly increased, and we've done nothing at all to the microscope other than turn on the laser and actually go to a new field of view, because after you look at something, you have done too much radiation damage to really meaningfully look at it again. So these are two images of clean fields of view of a purified sample that kind of just looks the same as you scan around within it. And then we did the same thing for ribosomes, which are these somewhat bigger proteins, and you can see they have even more contrast. And so for context, both of these samples are actually relatively easy for modern electron microscopy to study, even without the phase contrast. So even in this image on the left, they can actually make sense of it and get atomic resolution structures. But this is a huge protein. The ribosome is quite a bit larger than most proteins, which are not able to be imaged by cryo-EM at all by this technique, because they're too small. So as you reduce the size of the protein, this thing is just going to fade into the noise. And if you look at a really small protein, you'll just see noise, and it won't mean anything to anybody. So one of the goals of this project is to look at smaller proteins than we have been able to see before, and also to look at more complicated fields of view. So a lot of this, sort of going back to the point I was originally making about looking at context, this is an example of a cell that's been sort of popped and its guts have kind of been strewn about. And people want to know about the interactions between the different components of the cell. And so in this example, there are a few black dots that you see. So these are just gold beads, so they scatter a lot. So you can actually see there, gold is a much heavier atom. You can see those as dark spots. But the thing that's actually interesting is all the stuff that you can barely see that's behind it. And if you turn on the laser, then, come on, there it is. Then you can see a great deal more contrast of the same field of view. In this case, we cheated a little. We did actually irradiate the thing twice. It doesn't have a sort of noticeable effect by eye, but it would affect the data. The point of this is really just to show you that looking at the same field of view, you can see a lot more detail, right? You can actually delve into this data and dig something out. So in the future, we're making one big upgrade to our microscope. So we have shown you how contrast can be enhanced using a faceplate. And then the next thing that we want to do is also enhance the point resolution. So in an ideal lens, what you would have is that all of the rays coming through the lens would focus down perfectly to a point. In real life, and especially in electron lenses, there is this spherical aberration, which is a distortion of these rays, so that rays, in this case, for example, the rays that are further away from the optical axis are getting focused harder, so they're sort of coming to a focus closer to the lens than the ones that are going through the center, and then that sort of blurs out the focus, and that reduces the point resolution of the microscope. And so what we're hoping to do is combine our faceplate with this aberration corrector, which is a series of lenses for the electron microscope. So that makes the microscope even taller. So now we got a whole new room. This thing is 3.7 meters tall. And then in this little section here, we'll transplant our new faceplate, hopefully like next week. And yeah, so then we'll have faceplate imaging with better point resolution. And that is kind of a big dream of the project. So I think that's everything for now. So we want to express our thanks to Holger Mueller, our advisor, as well as Bob Glazer, who is an emeritus professor who's worked really closely with us. And of course, this project has spanned about a decade now. And in that time, there have been a number of undergrads, grad students, and postdocs all working. And as we also have a number of collaborators in industry and in academia. That's a really interdisciplinary and sort of fun thing to do. You know, as I said at the beginning of the talk, already combining electrons and lasers is something a lot of people don't do in the first place. But on top of that, you throw in biology and there's all this image processing and you get to build your own custom hardware. So it's a really sort of, it's a lot of variety and a lot of mix of skills and interests. And that's one of the things that kind of drew me into it. I sort of come from a chemistry background and I gradually became interested in developing methods that help you see molecules better. And so that's kind of how I ended up doing this. Yeah, and I think Jessie can comment on.
Yeah, so I actually sort of came from the other, for my PhD, I did AMO physics. So that was, well, actually also using lasers, but to interact with atoms and molecules. And now I'm using lasers to interact with electrons. And I think really I was drawn to this project because I really wanted to be building something that, you know, had some, like, you know, if this works, it could be a big deal for biology, and, you know, people trying to develop drugs for various diseases. And so it felt really like a really meaningful project to be working on, and the interdisciplinary aspect was also very appealing, and it's really exciting. Yeah.
Yep. So,
Yeah. Thank you all for coming.
Okay. This goes back to like a slide from the beginning, but just so I understand so the whole point of this is to have phase contrast imaging, and the laser shifts it by half a wavelength. Is that right? And so are you taking two separate images, one with the shift and one without, or what is the shift with respect to?
Right. Okay. So go back to
Yeah.
it is a single image, so only this ever happens. And what this is it's shifting it with respect to your scattered beam. So this is the unscattered beam. We focus it down so that only this unscattered beam is focused to this point, interacts with the laser, and that's this phase shift here.
Got it. So the point is having the phase shift after the initial
It's-
unscattered.
Yeah, like
Got it,
after the
okay.
sample, yeah.
Okay, awesome.
Mhm, yeah, it's a good question. Yeah.
Yeah, it's interesting because the amplitude contrast is kind of the sort of alternative to phase contrast. And the reason that we are pursuing the phase plate is because it's been observed that the way that the atoms in the molecules interact with the electron is that they phase shift it. But if you were to see a lot of amplitude loss because of scattering, then you'd be also interested in the amplitude. So one of the things that you could do for samples that have a lot of phase shift and a lot of amplitude loss is take two images with and without the phase plate to get both of those components of the wave.
Okay, awesome, thank you.
Mine is just more of a practical question, which is, so basically the idea is that you're basically taking, you're getting more data per image. That's basically the application of the phase plate. You can get more high quality data, which means you don't have to take as many images, you don't have to damage your sample as much. So basically, how much quicker, between these two things, how many images would I have had to take of my left image to get to my right image by layering a bunch of constructions on top?
Do you want to answer
Yeah,
that?
yeah, that's an interesting question. So I think there's some subtlety to it because the information that you get with the phase plate turned on is not like just, I mean, in this, it's kind of illustrated as just the opposite. Instead of getting the amplitude, we get the phase. In reality, there is some subtlety to that in the sense that at different spatial frequencies, we'll get different amounts of that information. And that's actually something that the spherical aberration corrector will help address. But sort of to the point of your question, I think excuse me. Sorry. Bug or something. Wow. Sorry, what was your question?
How much more efficiently can I get an image
Yeah.
on my
Right. So for high resolution information, let's take the case of actually these two images. There is actually some amount of defocusing happening in both of these images, which is really getting into something we haven't talked about. But the high resolution information that we see is comparable to the high resolution information that you see here. It's the low resolution information, the sort of big, long spatial frequencies that we see a lot more of. And so in that sense, it's a little bit of an asymmetric thing. We get the same amount of this high resolution information. But for example, if you were looking at this field of view and you just didn't know where the particles were because they're too small to see in the first place, then you have some information, but you can't actually get at it. Whereas on the right, you can capture more of that. And actually with the spherical aberration corrector, what that also enables you to do is really get rid of any kind of loss of phase information so that you could really collect all of the phase information in the image. And in that case, you would really have everything there is to have pretty much. So kind of a ballpark is that actually at the low spatial frequencies, the image is about 100 times better. So you would kind of need to take 100 times as many of these images to get a similar amount of low spatial frequency information. Of course, you can't actually do that because you would completely destroy the sample. But yeah, that's sort of in the case where the phase plate looks like the best, it's about 100 times better at these low spatial frequencies.
I saw that chat on Zoom. Let's see if we can post a question on there. Mostly, I think someone says the wave review was really helpful.
Oh.
I have one last question, which is there any way to describe how the spherical aberration fracture works, like what kind of lens or whatever this is?
It's not very easy for me to describe. What I can say in one word is that you have to change the sort of symmetry of the lens. So instead of having a circularly symmetric lens, they make these higher order lenses. So in this case, it's a hexapolar lens. So it has this sort of triangular distortion of of the image. And the idea is that you would distort and then you would undistort. And in doing that, you're able to correct the spherical aberration in a way that you can't by just sort of changing the circular lens strength or something like that. So it's just a different geometry of these magnetic lenses, basically, with more higher order symmetry.
Let's thank our speakers one last time.